Let's bring our discussion over to the asteroids now, and these are going to be rocky planetesimals. Most of the asteroids exist in the asteroid belt of our solar system, and basically they're rock fragments, maybe some heavier metals in them. And what we'll find in conventional asteroids is that they're just not big enough to have these spherical shapes. We have asteroid 2014 J025, who's just rotating around in very erratic fashion. It looks almost like two rocks glued together almost. And so this will have this crazy kind of tumble as it rotates around. So coming back to this idea that they're not spherical, remember this distinction we just set up between dwarf planets and other small solar system objects out there. Our asteroids are these rocky things that have these weird shapes associated with them. Even with all their peculiar properties, some of the asteroids can still have moons with them. This is 243 Ida, who's only 60 kilometers wide this direction and approximately 30 in this axis, and it still has the moon Dactyl floating around bounded to it. We can categorize our asteroids even further down into three main types, and there's going to be our C, our carbonaceous, probably not saying that right, carbonaceous, still doesn't sound right, carbonous, let's go with that. I'm going to shortcut and just say my C-type asteroids. And then we'll have S-types and N-types. So what we'll say right now is that the C-types tend to be a lot of carbon in them, whereas our S-types are going to be basically stony silicous type material, where the M's are going to be metallics. And so the dashed line here is talking about whether it was differentiated. This is going back towards the origin of these different types of asteroids. What produced these asteroids? And those mechanisms is going to tell us whether it's differentiated or what we call primitive, just basic materials. So there's a lot in this diagram. Let's follow the top chain first for the C types. And the bottom chain will be our S and N type asteroids. So focus on the C's for now. What these asteroids originated from was bigger planetesimals. And through just natural gravitational attractions, these things were accumulating mass. Stuff was sticking onto them and gluing together if they were massive enough or wet enough in some cases. Now, over the lifespan of this planetesimal, eventually something catastrophic happened. Basically, instead of particle coming in and gluing together, it smashed it to smithereens. Now, the asteroid, or the planetesimals that formed our C-type asteroids were not too massive. They were this limited amount of mass and formed the C's, the Carnaxes asteroids. And this is definitely the most common type of asteroids we see out there. And of course, even though they're the most common out there, they're also hard to see. They have what's called a low albedo. Now, albedo is basically a measure of how bright the object is. For reference, our moon's albedo is 0.12, whereas our C-type asteroids can be just a little dimmer to our moon to significantly, only 0.03 in albedo. So the C's, we tend to find them on the outer edges of the asteroid belt, around that 3.5 astronomical unit limit. Coming back to our initial planetesimals, what would make the S and N types? Well, these planetesimals grew massive enough, they eventually started to get hot in their interiors. Hot enough for a little bit of geological activity, enough for differentiation to occur. So the heavy metals started to seep down into the core of this planetesimal and left the silicates on the outer layers. Well, these planetesimals either got gobbled up by the planets or smashed into each other, obliterating them and leaving this differentiated material split up. That leaves us the remainder of the S and N type asteroids. So the S are the second most common siliceous mineralogical compositions, basically the rocks that we like to think of. Whereas the M's are the metallic cores of these dead planetesimals, and this is finally the third most common type of asteroids we find. And they're going to be composed of metals like nickel and iron. So one of the reasons for this naming convention of M, nickel and iron, they're two of our natural ferromagnetic elements. Do you remember the third? It's cobalt. Another asteroid that we'll focus on in particular is the Vesta Asteroid, which has about a diameter of 500 kilometers and is the brightest one in our solar system. And its brightness is due to the surface being coated with basalt material. Basalt is the fine material left over from, say, volcanic rock, volcanic activity. So this is an indicator that Vesta must have been a differentiated object, but Vesta isn't massive enough for differentiation to happen in its core. It just doesn't have enough raw mass there to squeeze things and up the pressure. But we've found even chunks of this. A chunk of Vesta has crashed onto Earth, survived the trip through our atmosphere, and so we've retrieved this meteorite sample of Vesta and have confirmed that these basalts are on its surfaces and that it, at least in some way, had some kind of volcanic activity on it. So, I propose the question to you. If there's remnants of volcanic activity on this asteroid Vesta, what does that mean? What does that indicate about it? So, as always, pause the video, think about it for a little bit, and come right back. Vesta was once part of a protoplanet that got shattered by collisions. Let me write a few slides back. And think back to our image here. These planetesimals, some of them got big enough to be that hazy range between just being a big object versus a protoplanet. And if they smashed together, that could have obliterated this protoplanet. And so Vesta is very likely the remnants of one of these objects. Another group of objects of particular interest to humanity are these near-Earth objects, or NEOs. Basically, any object that comes too close and is too big to be of major concern for us. So, comment that I want to make about the terminology here. Near-Earth objects is just this broad category of anything flying around, floating out there that could potentially hit Earth and have catastrophic consequences. And as you look around, you'll see the acronym change depending if you're referring to a specific object. Here's the near-Earth asteroid Tatus, a simulation of what it looks like, and it gets a claim of a NEA, near-Earth asteroid. So NEOs is the broad category, the big term. NEAs will fall under that. You can think of NECs, near-Earth comets that fly through. So just keep that in the back of your head as we go through this language here. For the NEOs that we'll talk about in this section, we'll say that too close is anything that falls within 1.3 astronomical units, and too big is anything that's about a kilometer wide. Anything about a kilometer wide, if it impacted the Earth, would have catastrophic events, not in just the area it hit, but globally. NASA in 1998 set up the Space Guard Survey, which has the explicit goal to try and find 90% of NEOs or NEAs that are floating around out there. And so what you're looking at is a plot of the dates that they're finding these things, and they've broken up into two categories. The red ones being the kilometer-wide objects. These are the world-ending collisions if they ever hit us. And the other category is basically anything that's 140 meters or greater. If your diameter is less than 140 meters, then it's very unlikely for that object to hit the surface of Earth. It will burn up in our atmosphere. But between 140 meters and a kilometer, that's big enough that it can probably get through the atmosphere and smash down into the surface. The blue is just the sum of the two. So as time goes on, as our tools and techniques get better and better, we keep finding more and more of these objects. Now, how can we be certain that we find 90% of NEOs? Well, that's based on calculations of basically the amount of mass available in our solar system. As of today, there's over 20,000 known near-Earth asteroids. And here are some simulations of them floating around around our solar system here. Good news is, we're not too worried about these things. None of these objects have any orbital paths that bring them close enough to hit Earth, at least in the time span of human civilization. But just keep this in the back of your mind that yes, there are a lot of objects out there pretty close to us.